Hello, my name is David Silver. I am the team lead for the self-driving car nanodegree program here at Udacity.
Hey, I'm Aaron Brown. I'm a content developer, and I helped build a project that we're going to be walking through today, which is path planning.
That's right. This is the walkthrough for the path planning project, which is the first project in Term 2 and the only project in the path planning module of the self-driving car program. So let's get started. Aaron, you built this. Where do I get started? Should I get started in the classroom?
Yeah, so let's go ahead and get started by checking out the project repository.
Okay. All right. Well,
we can just
Udacity path planning project, and that should come up on Google, right? Yeah.
Yeah.
Okay.
First hit.
First hit. Okay.
Cool. This will have all the code that we need to get started, including the link to download the simulator.
Okay. So let's see. I've already downloaded the simulator, so we download the simulator. What should we do next?
Well, we can actually just clone this repository over.
Okay.
And start building some code for our path planner.
Got it. So we could clone the repo. I've already done that as well here in my terminal. I am in the CarND path planning project directory, actually within the source subdirectory of that project.
Okay.
So what next?
Well, in source, all your main code will be coming from main.cpp.
Okay.
There's also some instructions in the README as well for just getting started, and what you kind of need to be thinking about when you're going from your simulator to your C++ code.
Okay. So here we talk about coding the repo, we talk about how to build the repo, and how to run it. So
yeah,
I have, just to make sure I'm all kind of in an original state, I'll check out main.cpp from the repo. I'll come over here. I've already run CMake, so now I can just make the project as is.
Make sure it compiles.
Make sure it compiles, and I'll run the binary. So now we're running the path planning binary. I'll swipe over and let's run the simulator.
Yeah.
So what's going to happen?
The car is just going to sit there.
Oh,
it has an empty list of XY points.
That seems disappointing.
Yeah, so we need to add some XY points to our planner.
Okay, so how do we do that? Should we go to the classroom? Should we do something else?
Well, let's open up main.cpp.
Let's open up main.cpp. Okay.
When we first open it up, we'll see a number of helper functions that we have at our disposal.
Okay, let's look at those helper functions. So, all right, let's look at the helper functions. There's a hasData helper function. Are we going to need this?
This is actually something that comes from our uWebsocket template
okay,
that we've seen in other projects before.
Okay.
We have distance.
So that could be helpful. So that's calculating Euclidean distance between 2 points?
Yeah, a lot of geometry is happening in this project.
Okay.
Closest waypoint. We have a map of all these waypoints around our highway.
Okay.
We can see which one's closest to us.
Okay.
We can see which is the next waypoint.
What's the difference between the closest and the next waypoint?
Because you could be right in front of a waypoint, and your angle is telling you that you want to go to this one that's further out, instead of the one that's closer to you but behind you.
Got it. It's like on the airplane where the nearest exit might be behind you?
Yeah.
Got it. Okay. Let's see. Get Frenet.
Yeah, so in the path planning lesson, we talked a lot about Frenet coordinates and how they can be really helpful, especially on a highway. So we have these transformations from going from Frenet coordinates to XY coordinates.
Got it. And what are the arguments here? There are 5 arguments. What are they?
We kind of have the ones that you'd expect, like X and Y. We also have theta, because this is helpful for actually doing the transformation if we look at the math. And we also have these list of X and Y waypoints that we calculate at the very beginning.
Got it. Okay.
Yeah.
So which of these do we need to worry about, and which of these or do we just kind of pass in without thinking too much about?
X, Y, and theta.
Okay.
And basically just use whatever we calculated at the very beginning for the maps X and maps Y.
Okay.
That comes from a file
Okay.
for the map.
And do we need to worry too much or at all about what's going on inside of Git Frenet, or do we just use it kind of as a black box?
You can use it as a black box, but the code is definitely there where you can actually modify it. Maybe you can even make it better. Maybe you have a different idea for how you want to do the transformation.
Okay.
Yeah, there's a lot of freedom there.
Okay. So let's see.
We did Git Frenet, and this is Git XY.
Got it. So
this
this
should
is
be
just
the inverse, except that Frenet and XY are not completely, it's not a linear transformation exactly.
Got it. So instead of passing in x and y, we pass in s and d, which are the Frenet coordinates. And instead of passing in theta, we pass in this this vector maps s.
Yes.
And then again, maps x and y. Is maps s something we need to worry about, or is that just kind of
That's
a
something
given?
that's calculated at the very beginning that we can just feed it, and that's just used for the math inside the function itself.
Got it. Okay. And now we get to main. So those are all the helper functions. This is main. And there's looks like there's a lot of variables being declared here. There are a couple constants. There's the CSV file. There's the length of the track, it looks like.
Which can be helpful when you're wrapping back around.
Okay.
But we just go ahead and we open up that text file of our map and we load up our vector of doubles of x, y, s, dx, and dy. dx and dy is just that normal component to that waypoint.
Got it. Where do we open up the CSV file?
It's actually just coming from data, and it's called highwaymap.csv. So we're using our string stream to actually load that up, and then
Got it. So that's done for us. This is,
that
okay.
then we can just use it throughout the program.
Okay. Let's see. So now there's some message passing.
Yes.
What's going on here?
Once we get past the usual uWebSocket template, we actually get our localization data.
Okay.
So the simulator is telling us exactly where the x, y, and SD Frenet coordinates of the car are at.
Okay.
Along with the car's angle and the car's speed.
Okay. So there's this if of n equals telemetry function, and is this basically where the action is happening?
Yeah, so this is all the variables that we're going to be working with in order to decide how we want to be creating and generating points.
Got it. Okay. So a bunch of variables getting defined here, some JSON stuff getting defined.
Sensor fusion's pretty important as well, so we talked about localization. Sensor fusion's all the other cars on the road with us that we don't want to crash into, that we want to try to pass when possible.
Got it. So there's this to-do here, and it says define a path made up of XY points that the car will visit sequentially every 0.02 seconds. And then underneath the to-do, we are setting some JSON variables, it looks like, equal to our X vals and Y vals, or next X vals, next Y vals.
And that makes up our path planner.
Got it.
X and Y points.
So in order to get the car to move forward, we have to set these next X vals, next Y vals to something, because right now we're just declaring them and immediately we're
Yeah, hence
We're
the reason
using
our
them.
cars is sitting still at the moment.
got it. So there's nothing in these vectors, and so the car's not going anywhere.
Right.
Okay. So how do we make the car go somewhere?
Well, there's some starter code in the classroom.
I was hoping you'd say that. All right. So this is the first concept in the classroom. There's a kind of cool GIF here. Talks about the 50-mile-an-hour speed limit.
Yeah, and that's kind of illustrating the perfect controller. The car is just going to go exactly at the point that you give it, and its angle is going to line up to the points.
Got it. Who really cares? I just want to get my car to go somewhere.
Well, luckily it's only like 6 lines of code.
Okay. These 6 lines of code?
Yes.
These 6 lines of code. All right. Let's type these in and see what we get. So
Yeah, go ahead and copy that.
just copy these in. So maybe I'll put these down here. Maybe I'll just put end here. And just get the formatting a little bit better. All right, so let's see what's going on here. We have a double called distance increment, I guess that is 0.5 meters. Is that
Yeah,
meters?
so that's how much the points are going to be spaced apart.
Got it. And why 0.5? Is that because this is 50 miles an hour basically, or?
Yeah, it's pretty close to 50 miles per hour, it turns out to be.
Got it. And then we're iterating through a loop 50 times.
Yeah, so we're going to be using a constant size of 50 points for our path planner.
Got it. So the next x vals vector and the next y vals vector are each going to have 50 numbers in them. So that'll be 50 points total when you combine the vectors. And each time we're just pushing back kind of this weird calculation, car x plus distance increment times I times cosine of degree to radian car. Yeah, what is that doing?
Oh, that's just a little bit of trig right there. Since our car has some angle, we just want to be going at that angle constantly in a straight line with constant velocity.
Got it.
Constant velocity comes from the fact that we're using just that distance increment.
Got it. So if I make this and run it, the car's going to go in a straight line?
Yeah.
Do you promise?
Yeah.
Okay. Let's see. I should have set that beforehand, but all right. So let's run our path planner. Go in a straight line.
Yes, but
Cool.
we're seeing a bunch of red flags popping up, right?
It's all right. We ran through a tree. Okay.
First of all, we're going from 0 miles per hour instantly to about 50.
Uh-huh.
That's going to create a lot of jerk.
Right. Okay. So what do we do next?
Well, now we can actually try to maybe either stay in our lane. That would be nice.
Staying in the lane is nice. So let's see. Could we use Frenet coordinates for that?
Sure.
So let's see. We're creating this
We have this constant list of 50 points.
we have this list of 50 points.
But these are XY coordinates. What if instead we're using SD coordinates?
Okay, so let's try and push new XY coordinates onto the vectors that keep us in our lane instead of just driving us straight off the road.
Right. If we want to try to stay in the lanes, Frenet is going to be very helpful to us.
Got it. So we could have something like double next S, and that's going to be like get, or double, sorry,
We can start with the car's S.
okay, got it. So we would do double get XY, or double get,
Well, we'll use get XY a little bit after the next S.
got it. So,
Get XY will be actually using our next S and next D.
got it. So we'll do something like car S time or plus I times distance increment. So the car's got a certain S coordinate and Frenet coordinates, and as we iterate through this loop, we want to step forward another distance increment each time. Is that right?
Yes, except for instead of just I, we want to do I plus 1.
Why is that?
Otherwise, our first point will be exactly where the car's at, and it won't be transitioning.
Got
And
it.
it'll be sitting still.
So, got it. So we could do I plus 1. Got it. Okay.
Yeah. Now, what do you think about next D?
So double next D. We are in the middle lane, if I remember right, and the waypoints are measured from the double yellow line in the middle of the road. So we are like 1.5 lanes from where the waypoints are.
Yeah, that's right.
And I think I read in the classroom that the lanes are 4 meters wide. So if we're 1.5 lanes away from where the waypoints are, 1.5 times 4 meters wide is 6.
Yeah.
So I'll just set that to 6.
Yeah, so that's what's really helpful about Frenet, is if we just want to stay in this constant lane, or
Got it.
D is constant as well.
Got it. Okay. So
Now we're actually ready to create our vector of XY.
Got
And
it.
get XY function will help us with that.
got it.
So it'll be a vector.
Yeah. Let's go back and look at that. I kind of forgot what the signature of that get XY function is.
Sure.
So if we scroll way up, and we look at get XY. So it takes SD, it takes maps S, maps X, maps Y, and it passes back a vector of doubles.
Yes.
And I
which
assume
is
that's
just
two doubles,
Yep, just your X and Y.
1X, 1Y. Okay, so let's do that. So we'll have maybe vector double xy equals get xy, and that's going to be next s, next s, next d, maps s, maps.
Of course, it'll be called something a little bit different than maps S.
Oh man, you're so tricky.
Yeah,
Where
that was an
where is this-
abbreviation. So right there, map waypoints S
Let's see.
on line 195.
Just going to look for where you declared it. So you declared map waypoints x, map waypoints y, map waypoints s.
Mm-hmm.
Okay,
The function was using an abbreviated handle.
got it. Okay, so map waypoints s, map waypoints x, map waypoints y. Okay, so now I've got x and y,
Cool.
and if I just push them on here, so next x vals is just going to be the first element in xy, and then we'll push the second element in xy onto the y vector, so the next y vals vector, xy 1. Okay.
Yes.
So we'll save that. So far, so good.
Mm-hmm.
Let's see, you think it's going to make?
The suspense is killing me.
I did it. All right, path planning,
Yep. Let's see how it runs.
let's do it.
We expect it to stay in its lane this time.
Oh, it's staying in its lane. There's still
Yeah.
a lot of red, but it is staying in its lane.
Yeah, so let's kind of talk about what's happening. So it didn't take too many lines of code just to get to stay in its lane, but it's a very crude representation of these points. We're relying quite a bit on the get xy function, and it works pretty well, except on these boundary cases. Our map is made up of these sparse waypoints,
Okay.
and we kind of have these corners and line segments. At these corners, these points tend to get kind of bunched up, and that's going to cause some acceleration and jerk issues.
Got it. And it looks like we're violating the speed limit. The speed limit's 55 miles an hour, and the
That's
speed
because
limit's
we're
50
still
miles an hour.
using 0.5. We
Got
could
it.
fix that maybe by doing 0.4, but
Let's start with that and see what happens.
we're really harassing the other cars on the road as well.
not a good driver. Okay, so let's take a look at. So if we just shorten distance increment to something like 0.3, is that going to solve our speed limit problems?
It will help the average speed. It should be much lower, but there'll still be times on those corner cases where the points may get bunched up and their spacing is a little weird,
Got it.
just in that transformation because it's not exactly linear.
Got it.
So
So the average speed is a lot lower. We're like at 33 miles an hour now.
Yeah,
And we're not violating the speed limit that often, but every once in a while it does say we're violating the speed limit.
yeah, and we can kind of visually see that on those corner cases. It looks like the points are, for the most part, all nicely spaced, except there's like this edge.
Got it. So now we've got the car kind of driving slowly in its lane, but there are these kind of inflection points where all of a sudden the car jerks and
Yeah.
maybe even violates the speed limit.
What we really need to do is smooth out that path.
We need to smooth the path. So how are we going to do that? There was a lesson on jerk minimization in the trajectory generation lesson. But I saw in the classroom you mentioned something about splines.
There's this awesome spline library that we can take advantage of. And it's
Okay.
not too far-fetched from what we're doing in previous projects like MPC, where we're using a polynomial that
Okay.
fit through waypoints.
Okay.
There's some advantages of a spline over a polynomial, where the spline is guaranteed to go through all the points because it's a piecewise function of polynomials.
Got it. So here's the spline library in the classroom. So I remember in college, I took a whole class on numerical analysis, and my memory is like a third of the class was on splines.
Okay.
There are all sorts of weird ways to calculate splines. There's piecewise functions that go through points. They're kind of like polynomial fits, except they go through all the points, and they're guaranteed to kind of have smooth transitions through the points.
Yeah, it's first and second derivatives.
Right. Why use splines instead of polynomial fits?
Because we have this library here that'll make it very easy for us.
Got it. So somebody wrote the code, so we're going to use splines instead of
It's in
polynomial
a
fits.
single header file.
It's a single header file. Okay. So we've got this header file here. We'll download it. I think I've actually already done that. Let's take a look in our source file. Source spline. Yep, it's already there. So so if we come over here, we'll have to add it way up top in our includes list.
Yes, includes spline.h.
Got it.
But you could do polynomial fitting here too. There's a lot of freedom when it comes to building this path planner.
Okay, but I like code that someone else wrote for me.
Yeah, it's kind of nice.
So let's see. Do we have splines.h in here anywhere?
No, you'll need to include it.
Okay, pound include. Do you remember, is it spline.h or splines.h?
I think it's just spline.h.
Spline.h?
I want to say.
Okay, shouldn't have cleared my bash history here. ll source spline.h. Okay, so now we've included spline.h, and we're still, what we need to use spline.h for is smoothing out that kind of disjointed path that the car was following in the simulator.
Yeah.
Right?
So I like your solution, but I might try to do something a little bit different.
What would you try and do?
Well, I might actually try to create some points, just a couple, that are pretty far spaced, maybe 30 meters or so, and then
Okay.
use a spline to fit that, and
Got it.
then actually try to take points inside that spline.
Got it. Okay, so let's try that.
Okay. I just so happen to send you some code that does that.
Oh my goodness. Okay, let's switch to your file. I think I saved that in the source directory, aaron.cpp. I don't know why I tried to cd. Source aaron.cpp. Now we copied that over to main. So now you've got this main
And
CPP
I already got
file.
spline.h included in everything.
Oh, you got spline. Man, you're way ahead of me. Okay, so let's scroll down here and then maybe you can kind of walk us through what's going on.
Yeah,
so
definitely.
Let's get to the to-do, or we can just search to-do.
We're almost there. Int main.
Almost there. Oh,
Huh. We're very close. Okay. We're doing what we were doing last time and collecting all those map waypoints. And
let's see. So if telemetry, then you've got some commented code here.
yeah, we'll kind of go through that later.
Okay.
But
right.
we'll keep things as simple as possible for right now.
Okay.
All we want the car to do is stay in its lane and go at a constant velocity
Okay.
and try to be as smooth,
Okay.
not violate its acceleration and jerk.
Got it. So what are you doing here?
Well, start out with, I'm going to actually come up here and define two variables.
Okay.
These two variables are my lane. So I'm going to start in lane 1. I can use this so I can quickly switch to other lanes if I need to.
So lane 0 is kind of the far left lane, lane 1 is the middle lane, lane 2 is the right lane?
Yeah,
Okay.
exactly. And then I'm also going to be telling it some reference velocity. Right
Got
here,
it.
I just kind of want to go as close to the speed limit as possible. I don't want to go over it, so I'm doing 49.5.
Okay.
And once I come into here and I get past just getting some of these variables, I'm going to be setting this previous size, which comes from the previous path size. So I have this previous list of points, and that can really help me when I'm doing a transition.
So this is the last path that the car was following before it does this particular run through of calculating more points.
Yes, and the
Okay.
simulator will actually be telling me what that previous path was.
Got it. Okay.
So let's kind of scroll down here.
So will that be 50? Because the path's always 50 points?
You could even do 100. You could do 1,000. You have a lot of freedom to have this path planner do as many points ahead as you want.
Got it.
And there's some advantages and disadvantages to doing that.
Okay.
If it gets stuck at 1,000 and you're using previous points, maybe there's some sudden change
Got it. Okay.
in the environment, and it wouldn't be able to react in time because it's stuck using those previous points.
Okay.
So I was kind of saying that I kind of want to use these sparsely spaced waypoints. So I'm just going to create this vector double list and kind of build from there. Also, I want to keep track of my reference state. It's either going to be where the car's at, or it's going to be at this previous path's endpoint. So I defined this reference x, y, and yaw. So x, y, and angle. Now I'm just going to check out what the previous path size was. It's either going to be pretty close to empty, or it's going to have some points that I can take advantage of. If it's pretty much empty, I'm just going to use the car's state. So right here, I'm interested in creating this path that's tangent to the angle of the car. So I'm going to be looking at where the car is at, and I can just kind of go backwards in time based on its angle, and I can generate 2 points to make sure that path is tangent. So that's if I'm just starting out and I don't really have any previous path points. If I do have some previous path points, I'm just going to be doing the same thing, where I'm going to make sure it's tangent by using the last point in that previous path and its second to last point. And I'm just going to be adding this to my points x and points y. I'm also going to change this reference x and reference y to the last element in the previous path. And then go ahead and calculate it just using our friend arctangent.
Got it. So basically what you're doing is you're looking at what were the last couple of points in the previous path that the car was following, and then calculating what angle the car was heading in using those last couple of points.
Yeah.
Is that right? And then you're pushing them onto a list of previous points?
Yeah.
Okay.
So far, I've pushed 2 x and 2 y.
Got
points.
it. So you've got 2x or you've got 2 points basically on this pair of vectors.
Yes.
Okay.
And now that's my starting reference, and then here's some other points. And I'm using Frenet. This is kind of what you were doing before, but I'm just making sure that they're spaced pretty far apart.
Got it. So instead of just looking out one distance increment, you're looking out basically 30, 60, 90. And instead of looping through and creating 50 of these, you're just creating 3 of them.
That's right. So I'm going to be pushing 3 more points, but instead of just them being 0.5 meters spaced, they're all the way to 30.
Got it. And where I had 6 as the d coordinate, you have 2 plus 4 times lane. Lane here is 1, so 2 plus 4 times 1 is going to be 6. But if you ever change the lane variable, that would
that can be very helpful too.
Got it. Okay.
Yeah. So go ahead and I push those points.
So what is this? What do these vectors of points have now? They have the 2 previous points, plus they have the car's they have the location of the car in 30 meters basically, and then in 60 and in 90 meters.
Yes.
So it's got 5 points on it now, right?
Right.
Okay.
Okay. Now this is something that's actually very helpful to do that I found, and that's doing a transformation to this local car's coordinates. This is something that we did in MPC. We shift it so we make sure that the car, or the last point of the previous path, is at 0, 0, the origin, and its angle is at 0 degrees. And this will come into play later, so just bear with me maybe.
Bear with you. Okay. So we're taking, if the car is heading this way, kind of in XY coordinates, we want to shift this so we're looking in the car's reference frame, so it's just kind of going straight ahead. Instead of being at 45 degrees, maybe it should always be at 0 degrees.
Makes the math much easier to work with.
Makes the math easier. Okay.
Okay. So we do that transformation here. It's a shift and rotation.
Okay.
So this is some of the math you might recognize from MPC.
Okay.
Here's that spline that we've been building
up
up
to. Oh, back to the spline. Okay.
Yeah. So I define a spline S, and then I simply set some points X and points Y to the spline.
Okay.
And here is actually where I'm building what we're working with last time. Next X vals, next Y vals. These are the actual points that the path planner is going to be using.
Okay, so we have this one set of X and Y points, and now we've got this other set that's empty at the moment that we need to put we need to build the future path in.
Yes.
Okay.
So we're just getting that all set up. We've been talking a lot about the previous path, and here's where it comes into play.
Okay.
So if I have any points from my previous path, I'm just going to go ahead and I'm going to add them to my path planner.
Got it.
This kind of helps out with the transition. So you make sure that instead of recreating the path from scratch every single time, why not just add points onto it and work with what you still had left from last time?
Got it. So if the previous path was 50 points, then there are always going to be 50 points here that we add on?
Yeah. That's what we're kind of doing right here, where we have 50 minus the previous path x dot size.
Got it. Isn't this 50 minus previous path x dot size always going to be 0? Because previous path x dot size is 50?
Previous path size will be less than 50. Let's say that you're running an iteration, you generate 50 points. Maybe the simulator goes through 3 of those points. So you have 47 left over that it's going to report the next time around. So now you have 47.
So previous path x is not the full previous path. It's whatever kind of Pac-Man nuggets in the previous path didn't get eaten up by the car.
Yeah, exactly.
So if the car ate up 3 points out of the 50-point path last time, previous path is going to have the 47 remaining points.
So we only need to generate 3 points.
Got it. Or if the car ate up 40 points, previous path will have 10 points left.
Exactly.
Got it. Okay.
All right. So we add on our previous path points. And here's where it gets a little bit interesting. I went ahead and I added these points to the spline. But I want to figure out how to space these points along the spline so that I go at my desired speed.
Wait, where did you add them to the spline?
So they're all added right here. I added points X and points Y to S.
Got it. So these are those 5 anchor points, not the previous path points.
Exactly. We're dealing with kind of 2 sets, if you will. We're dealing with our far-spaced waypoints that make up the spline, and we deal with our path planning points.
Okay, let's call the first set like the anchor points, so I can keep them straight. And then the second set will be like the next X vals or a future path or something.
Yeah.
Okay, so you've added the anchor points to the spline. Kind of in the middle here, you loaded up the future path with whatever was left of the previous path.
Exactly.
So that there's some continuity, I guess. And now we're back to looking at the spline and the anchor points. Is that right?
Yes.
Okay.
And this would be a great time to bring up some visual aid.
Okay, bring up some visual aid.
Yes.
Let's see, like that visual aid?
Exactly.
Okay, that's beautiful. Did you do that?
Oh, yeah. True artist over here. Here is our car in our local coordinate system.
Okay.
And you can see it's going at 0 degrees.
Okay.
This is kind of our spline that we have.
Okay. So
what I would love to get is these points that are spaced along the spline and spaced in a way that the car will go at the desired speed.
Got it. So you need these points to be kind of the exact right distance apart so the car's going 50 miles an hour, 49.5 miles an hour, whatever.
Right.
Got it. Can't you just look that up?
So I have to do some math.
Oh.
Okay. So, and I'm just going to linearize it, and it actually ends up working pretty well.
Okay.
I'm just going to do that by looking out some horizon value. Let's say 30 meters.
Okay.
And we can figure out where that point lies on the spline because we have this S function, and it's just f of x. We give our spline some x, and it'll give us some y. And we just calculate the distance from the car to this target point that I'm setting. We have this d. Here's where the math comes in.
Okay.
I want to split this up into n pieces. And it turns out that these n pieces times 0.02, because the car will visit a point every 0.02 seconds,
Okay.
times the velocity, this is actually my desired velocity, is equal to d.
Okay.
That's
Okay.
because this is in seconds. This is in meters per second. This cancels out the seconds. We have meters, and each end piece is some meters. And when
Okay.
we have all the ends, we get the full distance.
Got it. So that's velocity right there.
That is.
Couldn't quite tell what that was.
You
Okay.
couldn't?
That's a VEL for velocity? Got
Yeah.
it. Okay. All right. So what's the takeaway here?
The takeaway is that when we do this, we can calculate what n should be.
Uh-huh.
And since this is just a triangle, it turns out that since this is broken up into n for the hypotenuse, it'll also be broken up into n for this x-axis as well.
Okay.
And then once we have these x values, we just tell the spline, hey, what's the y value for this x? And we get these points.
So we just tell the spline, here's an x value. Can you give us the y value, the corresponding y value for this x value?
Exactly.
Got it.
And we just go through that for how many points we need, and we get x, y's along the spline.
Got it. Can you show that in the code?
Yes, definitely.
Okay.
So that's exactly what we're doing right here. That's our horizon going out 30.
Got it. Oh, there we go. Oh, sorry. Okay.
Our target y, like I was saying, we just ask spline, what's the y for that given x?
Aaron, this is Vim. You don't use the mouse.
Very true. And then we have this target distance. And that is just simply doing this distance calculation
Okay.
from the car, whether it be the last point of the previous path or the car itself, to that target.
Okay.
We have this x add-on, which starts at 0. And this has to do with that local transformation that we did. We start at the origin.
Got it. Okay. So here, target x is 30, and then we're getting the y value by simply, we've declared this spline, and now all we have to do is pass target x into the spline s. So up here, we declared the spline. Here we set the anchor points, and now all we have to do is pass in 30 to s, and we get back the y value.
Pretty easy to use the spline library.
I love when people write easy code.
So now we're just adding on those points that are along the spline.
Okay.
This is the math that I was showing in that previous slide. I'm
Okay.
trying to figure out what n should be. I have that target distance. I have this reference velocity. I'm dividing it by 2.24 because I was saying this was in miles per hour. It needs to be in meters per second. And then I have this x point. And that's just going to be whatever the x add-on was before plus this target x divided by n.
Okay. So n is what you showed us in the diagram, and now is x point. X point is each of those little hash marks on the
On the x-axis of that visual.
x-axis of that visual. Okay. So x add-on is kind of where we start. It's going to be 0, and then we're adding on our target x divided by n, which is the number of hash marks.
Yes.
Got it. Okay.
And then to get the y point, just ask
Got it.
what the
Got it.
y point is from the x point.
Got it. And so that tells us on the spline where is each little pearl or Pac-Man nugget or waypoint actually, such that they're far enough apart that the car goes the right speed. So
Yes.
got it. Okay. All right.
And in our case, we want to try to go at 49.5 miles per hour.
Got it.
So we loop through that. Last thing that we need to remember to do is we're in local coordinates. We
Okay.
need to go back to the global coordinates.
Oh, so like the basis transformation.
Yeah,
Okay.
so we just do the inverse of what we were doing before. So we're doing a shift right here and then a rotation.
Got it. Okay.
And then finally, we just push that back to our next x vowels and x y vowels, and we're done.
Man, you think it'll drive better than my car? It's a lot of work.
Yeah, let's try it out.
Okay.
And hopefully that one was saved, and we'll
Oh, did I forget to save it?
I don't know.
I guess we'll see.
We'll know right away, I guess. Oh, hey, there we go.
There we go. All right, so it is driving a little smoother. There was that thing at the beginning about max jerk exceeded.
Yeah, because we're going from 0 miles per hour to about 50 in 0.02 seconds.
Got it. So we're going from a dead stop to 50 miles an hour like
Yeah.
that. Got it. Okay. This is not my daily commuting car.
Yeah.
Okay,
A
so
little
what's going to
faster.
happen when it hits? Is it going to hit the car? Is it going to stop?
Right now, we're not checking if any cars are in front of us, so it'll actually just rear end this guy.
Oh boy, can we get a view?
Yep, there's
Okay.
the red flag for a collision.
Okay, so we got a few problems we got to solve here. One is the cold start. We're breaking our acceleration parameters on the cold start. And the second is checking for cars in front of us.
Yes.
So how do we handle that?
Well, first of all, it'd be nice not to hit the car in front of us.
Okay, all right.
Let's avoid doing that if we can.
Okay.
So let's kind of come up here, and you'll remember I had some code commented out.
Yep.
Now it's going to come into play.
Oh, I'd kind of forgotten about all that code you commented out.
Yeah.
Top.
So let's talk about sensor fusion now.
Okay. Tell me about sensor fusion.
Well, the simulator is reporting this kind of list of all the other cars on the road. And all these other cars have some S and D and X, Y, VX, VY values.
Okay.
We really want to use that to try to figure out where cars are at, how fast they're going,
Okay.
and how we should behave as a result.
Okay.
So right now, if we want to avoid hitting a car in front of us, we need to actually go through this sensor fusion list and see if a car is in our lane or not, and then how close that car is to us.
Okay.
And if it's too close, we do some action.
Okay.
So right now, I'm just doing this to help out. I'm looking at the previous size, or previous pass size, and if I have points to work with, I'm just going to change the car S so it's actually representative of the previous pass last points S.
Okay.
So I'm going to be doing this in Frenet, because actually it's quite easy if I work in Frenet for doing this kind of logic.
Okay. All right. So show me.
Okay, so for instance, I'm going to be looking at a D value here. D, I can think of as saying whether a car is in what lane.
Got it. So we're pulling sensor fusion is the vector of.
It's a vector of double.
Got it. And so the outer vector is storing like a list of basically car parameters for each car on the road, and then the inner vector is each of those parameters. So sensor fusion I is going to be the ith car on the road. Is that right?
Yeah, and also in the README, it kind of has this template of how you can access all the different data for that.
Got it. So I'm guessing sensor fusion index I, index 6 is well, obviously that's the sixth value of the ith car on the road, and the sixth value I'm assuming is the D value.
It ends up
in
being the
Frenet
D
coordinates.
value.
Okay. So now we have the D value, and we're running a for loop over all of these cars. So basically for each car, we're starting out a block in the loop by saying what's the D value of that car. Is that right? Okay.
That D value will tell us what lane the car is in.
Got
And
it.
We care about the car in this case if it's in our lane.
Got it.
So we have our lane, and we're just trying to see if it's in this range or not. If D is less than 2 plus 4 times lane plus 2, and D is greater than 2 plus 4 times lane minus 2. There's this plus 2 and minus 2 difference in the range because each lane is 4 meters. So we're trying to see, for instance, if it's in that center lane, is it between 4 and 8?
Got it. So we could just say is the car at 6, but that would only give us the middle lane.
Right.
We could just say is the car at 2 plus 4 times lane. That would give us any of the lanes, but it would only give us the center value, basically. Got it. So if the car's kind of in that lane but off center, we're going to need to check this range to see where the car is.
We could even make it narrow.
Could make
if
it
we want.
narrow, or if we.
Yes.
Oh man, too fast, too furious.
So if it is in my lane,
Okay.
I'm going to check out the speed of the car.
Okay.
I can pull that from Vx and Vy,
Okay.
which is the third and fourth elements, and then check the speed. So I'm just calculating the velocity magnitude of it.
Okay, so we're pulling the x velocity, the y velocity, and then we're running essentially the distance formula well, not quite. Yeah, essentially the distance formula to
get that magnitude of that
get the
vector.
magnitude of the
because
speed
we have
vector.
the Vx, we have the x and y components of that vector, but we want to try to get the magnitude of it.
Right.
And then we do a check car s is
Mm-hmm.
equal to centrifusion of this fifth element, and that's the s value of that car, and that's going to
Got
be
it.
pretty important to know whether that car is really close to us or not.
Got it. So now for each car we have, if it's in our lane, then we look further, and if it's in our lane, then we look at what's its speed and what is its s coordinate and front a coordinates.
Yes.
Okay.
That speed part actually turns out to be helpful for actually predicting where that car will be in the future.
Okay. So this, what is this line doing here?
This check car s plus equals.
Yeah.
So if using the previous points, we can project the s value outwards in time.
Okay. All right. So why would we want to project the s value outwards?
Because if we're using the previous path points, we're not quite there yet.
Okay. Got
Our
it.
car is still a little bit under that.
Okay.
So we actually kind of want to be looking at what the car will look like in the future. Because if we're using the previous path points, our path represents the future, but we're looking at this current snapshot of where our car sits and all the other cars. So from the perspective of the previous path, we want to say where those other cars will look like in the future.
Okay.
Yeah.
All right. So we're looking at where the car is in the future.
Yes.
Okay.
And then here we're just doing some more logic to see if our car S is close to this other car's S. So if the check car S is greater than car S, if it's in front of us, and if the gap is smaller than, let's say, 30 meters, then we need to take action.
Got it. So if our car in the future is going to be within 30 meters of this particular car in the future, then we need to take action.
Yes.
Got it. Okay.
So we need to do some logic here. It'd be great to lower our speed.
Okay.
We could even try to flag to say we want to change lanes.
Okay.
In this simple case, I'm just going to try to set the reference velocity down to 29.5.
Okay. All right. All right. Let's try it.
All right. Let's go ahead and save that. And
I don't think you saved it actually.
there we go. Awesome. Thank you, David.
You're welcome.
Okay. There it is. There you are.
There we go. Okay. Okay, so it's still exceeding the max jerk at the beginning, so it's still going from a cold start to 50 miles an hour, but that's okay. That wasn't the problem we were trying to solve here. The problem we were trying to solve was
Can we
problem
stop
of-
before we hit that yellow car?
Got it. It did say something about a collision there.
Yeah, it looks
Didn't
like
look like it hit anything, but okay. So it looks like it got up to that yellow car, and now it's slowing down.
Yes.
So it sees that yellow car 30 meters ahead or within 30 meters, and it's slowing down.
yes, it saw that yellow car. And we told it to go 29, and we never told it to speed back up again.
Got it. Okay.
So we detected it. and
Okay.
Took. Yeah.
Okay. So let's see. So I still want to solve the cold start problem.
Okay.
How do we do that?
Well, let's actually look at how we can do that. So here, all along, we've kind of been saying either go the set velocity or change instantly to this. Really, what we want to be thinking about it like is, can we do an incremental change of our velocity?
Okay.
Because we want to go at some acceleration. Maybe it's 5 meters per second squared, for instance. Then we need to be either adding or decrementing onto reference velocity.
Okay.
So instead of just saying, well, go 29.5, I'm going to comment that out, and I'm just going to set a flag here that says, you're too close.
Okay.
And then down here, I'm going to be looking at that flag. And if it's too close, I'm just going to be subtracting some constant value, 0.224, from the reference velocity. And it's not a magic number. It ends up being around 5 meters per second squared, which is under that 10 requirement.
Got it. So I don't fully understand how will this slow down the car at the very beginning? This looks like it only deals with slowing down the car if the car pulls up on another car in front of it.
Yes, there's one more thing that we need to do in order to address that,
Okay.
which is to come up here and start at, let's say, 0 miles per hour.
Got it. So we're going to start at 0, and
let's see how we can speed up. And that's actually included in our logic down here.
got it.
If the reference velocity is less than, let's say, 49.5, I'm just going to be adding on to it.
Got it. So if it's too close, and at the beginning it's not going to be too close because there won't be anything in front of it. It's just starting from a cold start with a bunch of road in front of it. But then else, if the reference velocity is below the speed we want to go, then start accelerating, but accelerate slowly, basically, is what you're saying.
Exactly. Now this will be doing that increment every cycle. We could be more efficient with that. We could come down to our path planner where it's going through every point and be changing reference velocity there.
Got it. And how does the reference velocity here affect the waypoints that get calculated later?
Yeah, so that actually affects our end value. If we come down here, we pass it to it. It's right here. We're using reference velocity.
That was tricky. I didn't even see that.
Yeah, so if we're actually adding or subtracting from reference velocity in this loop, that'll actually be a lot more efficient.
Got it. Okay. All right. So let's see. Should we run it and see how it goes?
Sure.
All right. Clear.
All right, let's take a look. There he goes.
Oh man, I thought it wasn't going anywhere for a second.
Yeah.
All right, let's see.
Thought the battery died on it.
Yeah. All right. So here we go. You can kind of see.
It's working its way up to that 49.5.
Got it.
We
All
didn't
right.
see any big red flags at the beginning there for
Nice
exceeding
work.
max acceleration or jerk. But now, here's the interesting part. Can we slowly decrease our velocity?
Okay. Man,
And
it's
we
getting
are.
awfully close. That path is getting awfully close to the white car. But the black car, our car, the ego vehicle, did not.
Do not crash into the
crash.
white. And
All
there
right,
it goes,
cool.
slowing down
This
again.
is awesome. So if we just waited for like 15 minutes, would the car make it all the way around the track?
Yes.
Awesome. But of course, it would be better to try and pass this white car.
Yeah, so maybe let's see how we can start thinking about lane changes.
Let's see. How can we start thinking about lane changes?
And this comes up a point of why I really love the spline library as well.
Okay. Oh, oops, sorry. All right. How do we think about lane changes?
When do you want to change lanes?
When a car ahead of you is going too slow and it's safe to change lanes.
And we have some logic to check if a car is going too slow, right?
We do. We slow down. We already showed us, like, if the car in the future is within 30 meters of where we're going to be in the future, then we slow down.
Okay, so maybe let's execute some code right there then.
Got it. So if a car in the future is within 30 meters of where we're going to be in the future, change lanes?
Yes.
Got it. Okay.
So
How do we
right
do that?
here, let's just go ahead and say if lane is greater than 0, we start out at lane 1,
Okay.
which is that center lane.
Okay.
Let's say that lane is equal to 0. So what should that do? That should actually make us do a left turn.
So if we are in the middle or the right lane, basically slam over to the left lane as fast as we can. I can't imagine what could go wrong.
In this case, yeah, we're just blindly going to be turning left.
Got it.
Regardless of
Shifting
if there's
left,
cars.
shifting left.
Yes.
Okay. All right. So let's see. So we're going to make this, and okay, we'll I keep thinking it's not going anywhere.
Yeah.
Okay, so let's get a good angle.
Definitely
Here,
don't
good-
want to take this one to the drag races yet.
Not yet. Okay, so the car is just doing its thing. We've seen this before. It's just driving in its lane. You think it's still going to pull up behind the white car, or it's going to pull up behind a different car this time?
Looks like it's that red one.
It's going to pull up behind the red car.
Yes.
Wow. Okay.
Let's see
All
what
right,
happens.
here's the red car, and
Whoa, that came pretty close.
But that was a pretty good lane change. It didn't
Yeah.
violate jerk limitations or anything. It just kind
And
of shifted.
The spline really helped out with that. It was interpolating between where the car was and 30 meters ahead in that left lane.
Got it. Show me in the code where that happened. Where
Yeah.
exactly was the spline interpolating the lane change?
Definitely. So we changed the lane right here. And if we come down here, you'll notice that lane is part of this that we're adding on to for the spline. So our
so
first
instead
2
of saying
points,
6 is the lane,
yes,
because you have 2 plus 4 times lane.
now
when
it's
you-
2.
When lane goes from being 6 to being 2, because the middle of the 0th lane is 2 meters out from the waypoint. So lane goes to being 2, so 2 plus 4, or sorry, 2 plus 4 times 0 is 2. So
Yep.
that's how the D coordinate winds up being 2.
Exactly.
Got it. Okay, and so then the spline waypoints are being set. So maybe the current waypoint of the car is at D equals 6, but then the waypoint 30 and 60 and 90 meters out is going to be at D equals 2, and so the spline will fit a
Yes.
polynomial kind of starting from 0, but then shifting over.
And
okay.
the
And it'll be
spacing-
smooth and continuous.
Yeah, and
Got it.
smooth and continuous because of the spacing too. Like if you were to decrease it from 30 meters, that lane shift could be a lot more aggressive.
Got it. Wouldn't want that.
Yeah.
Okay, cool. So this is pretty good. We've kind of figured out now how to do like a basic lane change. What about like some of the finite state machine stuff that we saw in the behavioral planning lesson?
Right.
How would we incorporate that?
We're doing something pretty simple for doing our lane shift.
Right.
But really, we might actually want to think about looking at other cars in that lane first, using similar logic to seeing if there's a car in front of us or not. Going back to Frenet, we can actually just check if a car is in that lane or not, and then we can check if it's in some gap range of S.
Got
If
it.
it is, then it's not safe to do that lane change. And maybe if it's not safe to go left, we can try to go right instead.
Got it. So you could have like a shift lane left or lane change left, lane change right, keep lane, and you would never enter like lane change left if you saw that there was another car within like 30, maybe 100 meters in front of you or 50 meters behind you, something like that.
Or if you're already in that leftmost lane.
Or
you
if
don't
you're
want to go
already-
off the road.
Right. If you're okay, so you'd start to add some logic around when do you shift to each of those states in the finite state machine.
Exactly.
Got it. Okay. Cool. That sounds good. I feel like that kind of gives us a good sense of like how do we get started with this
Yeah.
project. I mean, actually, I think that's like that would be, I think, a passing implementation of the project. I don't. Well, some of those lane changes might wind up colliding with cars,
Yeah.
so you might need to be careful about that.
Blind
But it
luck.
gets you pretty close.
Yeah.
So let's maybe let's move from that to answering some of the questions that students wrote in about.
Yeah.
And in the meantime, maybe
Let's pause for a second.
just watch the car drive. That was weird. Why did it?
Change lanes all of a sudden.
Yeah. Did it see something ahead of it? I wonder. Oh, maybe there was a car behind it that it thought was going to run into it. I mean, it was at a dead stop if there was a car right behind it.
I feel like it's because we didn't reset something on the C++ side.
Oh, that's probably true. But now we're in.
I think it instantly saw like,
Now we're in the far left lane and we can't do anything. We're stuck because all we know how to do is change lanes left if there's a lane to our left.
yeah.
Oh man, so we need a better finite state machine.
A good cost function.
and a good cost function,
Yes.
right?
Try to look into the future and see what's the best lane to be in 5 seconds or so.
Great. So let's go to questions. We got similar questions from several people. The first question we got a bunch of times in various forms from Sebastiano in Italy, from Jason, from Chris Edwards, from Nadia in New York, from Francesca Fantausi in Italy, from Michael in New York. Give a sort of walkthrough in order to face the project. Seems that the lesson and project lacks connection. Even in lesson, important parts are overlooked and concrete examples are missing. Very disappointed this time in how the course was structured. Lots of expectation, lots of delusion. Well, let it never be said that that we don't give you the straight truth from Udacity. We're sorry about the disappointment. We do think it's a really fun project. There may be some work we need to do in order to help connect parts of the lessons to the project, but in general, path planning is one of the most difficult parts, if not the most difficult part, of autonomous vehicle development. And so it does make sense, it's a lot of work. We want to try and connect it and make it a little easier. Hopefully the walkthrough we just did kind of gives you a sense of one way to approach the project. There are a bunch of different ways to approach the project. I actually, when I did the project, approached it a little bit differently than Aaron did. Aaron's drawing with the N and the D was a little much for me, so I tried a different approach. But I think at a high level, at least what I wanted to do with the project when I first got hold of it was just get the car moving, and that you can do with the code from the classroom. Then get the car to drive in its lane, and that turns out to be a surprisingly difficult problem. You can get it driving in its lane pretty well with just Frenet coordinates, and then the somewhat harder problem is smoothing the path, and I think there's a question coming up about smoothing, so we'll talk more about smoothing there, but that's what we did with the spline in this particular walkthrough. And then once you get the car driving in its lane, then you enter a world that looks a little bit like the quiz at the end of the behavioral planning lesson, where basically you've got your car in a lane and a few other lanes, and you're looking at how do you switch between lanes. And one way to do that, probably the preferred way, would be to build a cost function. That's not what we did here. Here we had just a very basic, if you see a car ahead of you, veer to the left. But overall, you'd probably want some sort of cost function that took into account what the cost of being in each lane is. And then if you kind of work backwards all the way to the prediction lesson, you can actually try and predict out into the future where all these cars are going to be at different points in the future, and what's your cost going to be for being in different states, in different lanes in the future. And so that's kind of how you might think about it, is kind of start by getting the car moving, and that's just trajectory generation, basically. And then you start to think about behavior planning and what state do you want to enter, change lanes left, change lanes right, keep your current lane. And then if you make it that far, predicting out into the future and trying to figure out where other vehicles are going to be with, say, a Gaussian naive Bayes classifier or a different type of classifier, and using that to decide where you want to be in the future. So with an actual path planner, the way the data flows in is you get the data, you try and predict where things will be in the future, then you try and make your own decisions in behavior planning, and then ultimately you generate a trajectory. For this project, you might almost want to work backwards and start with building a trajectory and assuming no other vehicles are there, and then start to assume other vehicles are there and build a behavior planner, but don't worry about the future, and then maybe worry about the future and start predicting out where other vehicles are going to be in the future, and thus where do you want to go. That's my take on it. What do you have to say, Aaron?
No, I think that sounds very good. We were definitely just dealing with the trajectory for the time being, but a cost function would be great for dealing with how to change lanes, and the quiz is a great place to really get started with that. And Frenet is very helpful for just being able to look at all the other cars on the road and seeing where their S&D is at. Frenet gets a little tricky when we're doing just pure trajectory generation. That's why we kind of had that spline come into play as well.
Got it. Cool. From Tim Toby in New Jersey, review implementation of spline. So we mentioned a little bit in the walkthrough what a spline is. It's basically a piecewise polynomial function that's where the pieces are tied together at those anchor points, or sometimes they're called knots. And some math is done in tying together those pieces so that the connections at the knots are smooth, which is why the spline trajectory looks smooth. I think for the perspective of, or from the standpoint of this lesson, you don't really need to know how to implement it. We're really just using it because the code was written and was there. It was really easy to use, and so all you really need to know how to do is use it. You want to walk through just real quick the different parts of using it. There are only like three commands to run when using
Yeah,
header
so you
file.
just initialize it.
Let's actually go here, maybe in the code, and look really quickly at how
Sure.
how you use the spline.
Yeah,
So here, this is when you're declaring it,
TK spline S.
right? So we included the header file, so now we can declare the spline. Now
S dot set points.
you're setting the points. So these are
X and Y.
the anchor points, or the knots around which the spline gets formed.
Mm-hmm.
And then
from there, it's just S and then some X value.
got
We
it. So you
get
give
some
the
Y
spline
value.
an X value, you get back the corresponding Y value on the spline.
Yeah.
Cool. One of the things you do have to be careful about with splines, just like you would have to be careful about with a quintic polynomial or anything else, is that if the spline starts to go vertical, you can wind up with like multiple X values or multiple Y values for the same X value, and that starts to break things. And so that's why Aaron did that basis.
The localization transformation.
Right.
Yes.
So that you're looking horizontal, you're shifting horizontally.
Makes the math easy.
Yeah, that way, if you shift the spline so it runs horizontally instead of vertically, then there won't be multiple Y values for an X, and once you pull out the waypoints you need from the spline, you can shift those waypoints back, and everything will just work. So we have a question from Doug in Redwood City, and also from Juan Pedro in Munich, from Constantine in San Francisco, and Oliver Hager in Atlanta. Can you talk about some strategies for smoothing the trajectories between the calculations? I'm able to generate a smooth trajectory by creating a spline based on waypoints around me. However, my jerk often exceeds the threshold when I create a new trajectory in the next calculation. Cool. So why don't you talk?
The previous path points, I'd say, is a great way, and that really helps you avoid any discontinuities. You got to be careful when you're purely just creating a new path every single frame. Mm-hmm. And having those previous path points really helps give you an anchor, a reference to work from. And I found that when I was having problems with my jerk, that I definitely needed to rely more on the previous path points.
Got it. So one technique for smoothing is the previous path points, using the previous path points so there's more continuity between the new path and the old path.
Yeah.
There's using the spline itself and picking out waypoints along the spline, because those are guaranteed to be smooth. You could do quintic polynomial generation, like is covered in the trajectory generation lesson. That involves a little bit more math. And if you're a lazy engineer, that spline header file is awfully tempting. In my case, I use the spline as well, but I also, instead of doing this kind of trigonometry that Aaron does with D and N and projecting from the spline onto a triangle, I basically went through, once I pulled off the 50 waypoints from the spline, I basically went through and verified that none of them were too far apart to create a velocity that was too high, and if they were, then I pulled them back in. That's probably a little bit less efficient than the math Aaron did, but I could wrap my head around it a little more easily. And it was, I think it's guaranteed to work a little better. Whereas I'm still not convinced this is actually guaranteed. It seems like it does work.
Yeah.
And that's probably 90% of the battle. I'd have to really sit down and go through the math just to convince myself whether it's guaranteed to work or not.
From Doug in Redwood City, California. When I used the live help feature, one mentor said that I should convert the waypoint map coordinates to vehicle coordinates and use this for all my calculations. Do you think this is a good approach? I couldn't figure out how to do that transformation. Yeah, I think that's an awesome approach, and that's actually, if you're talking about the local transformation, it's exactly what we did in our walkthrough here.
Let's see, can we see the code here?
Yeah, sure, let's take a look.
Here's
yeah.
the transform back. I know is going to be below. Yeah.
Yeah, that's the transform back. But there's the math to kind of just do the shift and rotation. And I believe that when we're first doing it, we're doing the shift first and then the rotation. And we can kind of scroll up here and check that out as well. Yeah, so we're doing the shift first here and then the rotation. I found that to be very helpful for a number of reasons. First of all, we're deploying that in MPC, and that made the math a lot easier. It also makes sure that you don't get any functions that are near vertical and that could just kind of explode on you. And for what I was doing to try to fit points to a spline, that actually made it a lot easier because then I'm just working with the x-axis. I don't have to try to create some separate line going at some angle and then work from that. So,
Cool. From Xin Cheng in Taiwan, how does the finite state machine work with hybrid A* in this project? So how does the finite state machine work with hybrid A* in this project? I think we had a debate about this early on. I think I won that debate. Did I win that debate?
yeah, I believe
I
so.
love winning. So is hybrid A*, does hybrid A* make sense to use for this project?
No. Hybrid A* makes sense more so like in a parking lot environment, but on this kind of highway, more a cost function makes more sense.
Yeah, I mean, the thing about the highway is it's a very sparse environment, so there are just a ton of different maneuvers you could make, and you just want to choose the lowest cost maneuver, whereas hybrid A* tends to work a little better in denser environments where you have a more limited number of choices you could make, and also discretized choices. And this is more of a continuous environment. You could like map a grid to the highway and use hybrid A*, and maybe it would work, but using a cost function, a finite state machine, seems to be a better choice here. I think maybe the broader point is, in general, I'm not sure that you would generally use a finite state machine and hybrid A* together. Maybe there's some interesting way to do it. There's probably some research paper out there that does it, but I can't think of why you would do that off the top of my head.
I'd be very interested if someone did use that strategy.
Okay. Chris Edwards in San Diego. In highwaymap.txt, why is S not redundant? It's so easily calculated, right?
Just included it in both, just in case. Also, there's that map waypoints S that we're fetching at the very beginning, so that's used in the helper functions.
Okay. It actually seems to me like it might be a little bit of work to calculate it. You definitely could. You'd have to do some vector math, though.
Oh, you could use one of the helper functions to get the S.
Oh, okay. Given the helper functions.
S
yes.
is included
Fair
all
point.
over the place.
Fair
It's in
point.
the localization data. It's in the waypoint, map waypoints.
From Ivan Danov in London, can we use Frenet for both trajectory generation and behavior planning? When to convert back to global Cartesian coordinates and how to avoid jerk caused by inaccuracies from the conversion? So I think you can use Frenet for both trajectory generation and behavior planning. For trajectory generation, you're ultimately going to have to convert back to XY global coordinates. And so how exactly you avoid the jerk gets back to what we were talking about a little earlier around smoothing operations and how exactly you read off the spline and what you do to minimize the jerk between the waypoints and the spline. From Juan Pedro in Munich, how to deal with the lack of precise acceleration readings from the simulator? Would inferring it from a set of consecutive points in the trajectory or measuring time between simulator updates and using changes in speed be sufficient, or are we better off just forcing end start accelerations to be 0 when calculating trajectories and only stitch together trajectories by their ends?
Checking out the acceleration values within your code could be really helpful. In the simulator, it's actually just averaging it from like a certain time, maybe say 1 second interval. So it's a little bit of an average right there. But if you're doing like the trajectory generation itself, such as the quintic polynomial solver, generally you're using 0 acceleration for both the start and the end.
Yeah. I think in general, if you want to guarantee that you're not going to exceed the acceleration limits, then calculating it and verifying that in your code is helpful.
Yeah.
But as you saw, Aaron's code worked fine, kind of assuming some things about the spline, and it just kind of worked. From Oleg in Austria, how do we generate trajectory in state transition function when we want to calculate cost for each possible next state? If the state is PLCL and we generate trajectory with horizon 5, what states should we take for the next steps? If you want to change lanes, you can calculate a few different candidate splines by using different anchor points, and you can calculate the jerk on each of those splines and then select the spline with the least jerk. That's kind of what's gone over in the trajectory generation lesson. You could use jerk minimizing trajectory, which is covered, JMT, which is covered in that lesson as well, although that uses a quintic polynomial, which is different than what we did here. Do you have any clever answers to how to generate the trajectory for a state transition function?
Yeah, I mean, I like the idea of using several different anchor points and then trying to actually calculate the acceleration change on each of those. That's definitely interesting. From what we're doing right here, we're just kind of had some sort of meter distance that we could use to kind of tweak, and that would actually change how aggressive our lane change was. That ended up working pretty well for me, but once you have that working from a low level, then you can kind of build up and define higher states like keep lane and prepare lane change left, and then you're kind of talking about that behavior planning quiz and having a cost function that goes along with that with a horizon.
Got it. Let's see, from Oleg in Austria, what logic should be implemented behind state PLCL, PLCR, so that's prepare lane change left, prepare lane change right. If target lane speed higher, then should we increase speed or track gap first? What if we increase speed and collide with a car ahead? If target lane's speed lower, should we decrease speed before lane change or shift and then decrease speed? There are so many options.
I think the safest is to decrease speed generally. If you're trying to get over in this lane, you pick out a car that you want to just kind of merge right behind.
Yeah, I mean, so the main reason you would use prepare lane change is if you want to shift left but you can't or shift right, but you can't because there's a car where you want to shift. And so that's where predicting out into the future and using what was taught in the prediction lesson becomes helpful, because you can see whether that car that's, say, sitting off to the left and blocking your ability to shift lanes, is that car speeding up, in which case if you maintain constant speed, a gap will open up for you to slide in, or is that car slowing down, in which case maybe you want to speed up if you can and get around it. But essentially you're just kind of predicting out the future and trying to figure out when a gap will open up for you and what the best way to fit into that gap will be. So there are a few different options.
That's kind of the meat of the project and really where
Right.
it can get quite interesting.
Right. I am confused about some codes from main.cpp. Oh, sorry. From Clio. I am confused about some codes from main.cpp where in the function of int next waypoint, I don't know what the angle variable represents for and why the angle has to be larger than pi greater than 4. It would be nice if you could explain a bit about how does the next waypoint function work. Thanks.
Yes.
Go for it.
So for that one, the angle is actually the car's angle, and that's just telling you basically which waypoint the car is looking at. We want to avoid getting a waypoint that's close to the car, but that the car is not even looking at. And basically that pi over 4, that 45 degrees is kind of telling you that range to look at. So there's a little bit of trig involved in there for just seeing if that waypoint aligns with that angle or not.
From Chris Chen in Detroit, what are the key software components to use for the project? For example, JMT, cost functions, FSM. What do we need to pay special attention to avoid violation of speed, acceleration, and jerk limit? So the key things that we used were Frenet coordinates and some sort of a path smoother, whether it's a quintic polynomial or a spline or something else, and then a finite state machine to figure out what maneuvers you want to take. So I think that's probably the minimum set of things you could do, but you can get kind of infinitely complex, and particularly adding states and trying to navigate through traffic as quickly as possible. Anything else you used? Nope. Okay. From Constantine in San Francisco, Jean-Francois, did I say that right? I hope, in San Jose. Can you suggest how JMT and spline should be used together to achieve a solution? I would say it's probably either or. What would you say?
Yeah, I think it's either or.
Basically, you're looking to smooth a path, and you can use JMT or a spline to smooth that path. From Frank Schneider in Germany, please explain what to use as theta in get-Frenet method. The heading of the car produces off S values when more distant coordinates are converted.
That's probably because of the nonlinearity of the transform, and we're seeing that kind of at those certain edge cases of the track, where if we have this kind of S and D value that are calculated close to when the car is at that edge, it might just be a little bit off.
I didn't implement that. Blame Aaron.
You can always change the math too.
Send the pull request. From Frederick, how to calculate S dot dot. So S is going to be our position in Frenet coordinates. S dot is going to be our velocity in Frenet coordinates. S dot dot is going to be our acceleration in Frenet coordinates. So if you think about how to calculate S dot, which is velocity, you basically want to figure out one point and then another point, and then we know the vehicle operates at 50 points per second, or the simulator operates at 50 points per second. So if you divide the distance you take the distance from one point to another point, and then divide that distance by 0.02, which is 50 points per second, that should give you the velocity. So that gives you S dot. And in order to calculate S dot dot, what you want to do is calculate the change in velocity. So you want to calculate the velocity between one pair of points and the velocity between another pair of points, and then divide them by the time it takes to get across that entire set of points, and that should give you S dot dot. And it would be the same in XY coordinates. It's just a coordinate transform. So, is that right? Did I get that right?
Sounded good.
Sounded good?
Yeah.
I'm pretty sure that's right. I'd have to sit down with a pen and paper and actually do the math. But I'm pretty sure that's right. You can cut out the last bit there. Yes, wrap up. So thank you so much for joining us for the... Thank you very much for joining us.
Give it a beep before you start. And action.
Thanks so much for joining us for the walkthrough of the path planning project. This is a really challenging project. It can also be a really fun project. You can do a lot of neat stuff with it. The work Aaron's done to build the simulator for this project and for a lot of the other projects is really, really fantastic. I think it makes the project a lot more fun than it would be if it were just decimals on a terminal screen. So I hope you have fun with it. I hope the walkthrough we did here gives you a sense of one or maybe multiple ways to approach the project. And we'll be in Slack and on the forums and amenable to answering more questions if you have them. So let us know if you do.
Yeah.
Cool. Bye-bye.
Bye.
Buddy. It is 3:15.
Man, that was a monster. Thanks.
Longer. Yeah, I was hoping we would. I don't think it'll be ready by 5.
Mm-hmm.